So today's actually a good lesson for April Fool's Day because we get to start with 20 questions. It's not even a joke. It's actually the material that we're meant to cover. So you probably all know the game 20 questions. Someone thinks of something, and then you ask questions that have yes/no answers, and you try to guess the item within 20 guesses, right? So we'll actually play it. Here's the example. You might ask, is it metal? Yes. Is it a tank? Yes. Game over. This is actually from a movie. Does anyone know what movie this is from? No one knows. Too old for you? Bill and Ted? I think it's Bill and Ted's Bogus Journey. Yeah. Okay. All right. So I have something in mind, and please ask yes or no questions to try to guess it. Do we what? Oh, no, you get nothing. You just start. What? Yeah, that doesn't count. Okay, let's ask real questions here. Go ahead. Yes? Is it an animal? No. Okay. What else? So the answer was no. Is it either a plant or a vegetable? So you want to ask, is it a plant? No. All right. Well, there we go. Who else? I guess I would have to say yes. Although you may not be happy with how loosely it's related. All right. I'll say it this way. So related to course. This is really kind of a very weak sort of. Okay. What next? Yes?
Is it a physical object?
Yes. All right. What next? Someone have a question for me? Would you find it in your house? No. All right. Is it metal? Not completely. I'll say no, although yes, it has metal. It's not a tank. Let's say no. Okay. What's next? Sure you'll get it. Baby steps. Come on. Another question? Do we have one? Is it as big or bigger than a shoe? No. Yes. Sorry. Yes, it's bigger than a shoe. Okay. Yes. Another question? Do we have one over here? Yeah. Is it used for what? Medical purposes? No. Okay. How many questions do we have? This is our 8th question. Okay. How about over here somewhere else? Do we have All right. Another question? Yes? Does it move? No. All right. Another thing? have another guess? It's not Euler. Does anyone look at the notes from last year? No. Okay, you guys don't read last year's notes. It was Euler last year, but it's very different this year. What? Okay. It would be considered, yep. No. The answer is no. All right. Come on. Just throw out guesses. We don't need to get stuck on this. Yes? Yes. I mean, maybe not every day, but. Okay. It's much more specific than you're thinking. It's not a generic object. Okay, giving you a hint here. All right. Go ahead. Yes. That's not its main feature. I'll say no. Okay. Yes. I think. Okay. It's not metal. Okay. Maybe you should go back to some size questions here. Larger than a person, yes. Oops. Okay, and the next one's building, and yes. Now you might know what it is. Okay. Who wants to take the last guess? It's the Friend Center. Yes. Okay, you got it. Only a little bit of hints, but you got it much short of 20 questions, so maybe you would have done it on your own. I'm just afraid if you'd have done it on your own, the class would be over, so let's see. Yep, that was 11 there, 15 questions. Wow, last year it was 15 questions as well. Pretty good to get Euler. Okay. So, great. Let's tie this into something we're learning. What was that? Hey, you meet here every day for the course. Imagine if I would have said no. I would get more complaints. Okay. All right. So the idea to this game, let's just summarize kind of how it works. You have objects that are picked. Now, really, I could have picked anything I want, but it makes more sense to talk about this as if I picked it from some very large set of choices. Obviously, if I go making up words, you're never going to guess it, right? So there's some set, and that's the set of possible things I could have chosen for the game. Here's an example. Could be things like monkey ball, apple, tank, and a whole bunch of other things, right? And I could have chosen those as the answer. And I want to know now, how large could this space omega be, and I still expect to be able to win this game each time? Okay, so in other words, so we say the size of omega is this. That's how many things could be in the possible answers, and yet this still be a feasible game. Okay, so that would be 2 to the 20. Why do we know? Well, we know if it's less than or equal to 2 to the 20, by the way, 2 to the 20 is just over a million. So about a million different choices. Now, really, there are more than a million things in the world, but maybe there's less than a million things people would think of to use for this game. Okay. So, well, how do I know? Because there's that many yes-no patterns, right? So there's that many combinations of yes/no answers, and I couldn't possibly resolve the answer down below the number of possible patterns, no matter what questioning scheme I use. All right. Now, what if there are less than 2 to the 20? Can I always win at this game? The converse of what we just said. We said it can't be more than 2 to the 20, but if it's less than 2 to the 20, is there a way to win? You say no. Okay, so you could design. Oh, I see. Well, let me say that you're saying if the questions evenly split the set. So that would be the strategy, right? Each question should split the set in half. And you're wondering whether a question can always be designed that will do that. If we could split the set in half every time, then yes, we could get to 2 to the 20. Well, you could construct crazy questions, right? You could say, is it either a tank or a ball, or list out half the set? That's still a yes or no question. So in fact, you can design it to always split in half. So really, there's our limit for this game. Now, what we're going to be interested in is not exactly this game. It's more of a game of trying to find the answer in the least number of guesses on average. Okay, so you're going to come up with some scheme that maybe finds your answer quicker. But as you know, if you try to find the answer quicker and you're wrong, then you kind of push more questions to the other options, right? There's a trade-off. But maybe you want to find you want to ask the least number of questions on average. Okay, and that's really what we'll be interested in. So let's take an example here. I'm going to just say we have some set. We know what it is. It's apple, orange, pear, and banana. And suppose we know the answer is in that set. Okay. First thing, it's the same question as above. How many questions do we need to get it? And just as above, we know that we need two questions, right, to figure out which it is here. Divide up however you want. Your first question can be, is it an apple or an orange? And then the next question, if that was yes, is it an apple? Okay. Now, suppose now that we actually know something about the probabilities that the person who's choosing the answer, there's certain probabilities that they'll choose apple as the answer. And we know that to be a half. Or sorry, let's say that one's a quarter. And probability of orange being the answer is an eighth. Probability of, I'm just going to use a P for probability. Probability of pear is a half, so it's the most likely one. And lastly, probability of banana is a quarter, an eighth, sorry, is an eighth. So these sum to 1, right? These are probabilities. Now, what we'll want to do is, like I said, come up with some question scheme that minimizes the average number of questions. So you can take advantage of the fact that, pear is the answer more often. Okay, so there's a suggestion. Suggestion is that you would first ask, is it a pear? I'm going to write a little tree here that branches according to your questions, okay? So you're saying, first question, is it a pear? Okay, so we have a yes branch and a no branch. The yes branch you end, because you know it's a pear. Good. But here you have to ask another question. So what's your second question if it's not a pair?
Wait, are you allowed to ask only about one object?
No, you can ask sets. You can say, is it this or this? Yeah, you could ask that. Exactly. You think that you would ask next, is it an apple? Okay, so let's do that one. Why did you choose that? Yep, it's the next most likely there. So great. So yes would be end. No, you still need to figure it out. And then the last one, we only really have one question left, so we could form it several ways. I'll say, is it an orange? And either one of these ends. Okay, so notice what we've done. Let me put the answers that we get when we get there. We get pear. And I'll put in parentheses, how many questions was this? Oh, sorry, no, I'll put that. That's something else. Okay, we get pear here. We know it's apple here. We know it's orange here. And we know it's banana here. So we're done. Now notice, we've now changed from, before we had a questioning scheme that only took 2, and now we might need 3. So maybe it looks worse because, in some cases we need 3 questions. But we calculate the average number of questions, and what do we get? Well, that's, so I'm going to use notation like this just to get us familiar with this. Let's let x be the answer. And let's say that L of x is a function that tells us how many questions we asked for that particular answer before we got to the end. So this function L depends on our strategy of asking questions. Above we have listed a strategy, and we're going to use, for this calculation, we're going to use the lengths associated with that strategy. Okay, so here's what we have. Let's say the average length, right, is the expected value of L of x. We talked about expected value last time. That's what we mean by average here. So that equals, we sum over all the possible answers. Okay, sum over all the x's. The probability that I defined above, it's not on the screen right now, times the length, right? So let's go through. Apple was a 4th, okay? And how many questions did we ask for apple? 2. Okay, now orange was an 8th, and we asked 3 questions. Pear was 1/2, and we asked 1 question. And banana was an 8th, and we asked 3. Okay. Now you add all these up, and you're going to get 1.75. Okay, so we indeed did improve on 2. 2 was the scheme where everything gets the same number of questions, and now we get less by prioritizing. All right. Turns out that this is the scheme that's optimal for this particular problem. All right, but what we're going to want to understand is what's optimal in general. Give me an arbitrary probability distribution. Can I find the optimal scheme? The worst case is worse here. So it's optimal in terms of the average length. Yep. Okay, so okay. All right, so I want to hear from you guys ideas for designing this scheme in average. We've done one example, but what about generally? How do we come up with a scheme based on the probabilities of all the answers known in advance?
So we are allowed to ask about half the set?
Yep, you can ask about arbitrary sets and say, is it in this set? You can define a set. In fact, that's the most general form of a question. When you play the game, you usually say, you start with natural questions that sort of roughly divide things in half, because they're easier to state, and that's how games are played. But there's nothing that prevents you from asking the most general form of a question that says, define this set. Is it in that set? That's the most general question. Yes?
So an idea for an optimal scheme would be to pick a set that is composed of like the smallest number of things with the sum probability of like a half.
Okay, so you would find a question that splits probably in half, but you have another part to that. Splits in half. So in other words, you have a 50% chance of getting yes or no. And you would also have make that question as small as possible. Make that question have the fewest number of items in one side. That means the complement would be the largest number of items you could fit. And I might ask, do you only, so you've given 2 parameters, you prioritize the first one, like find a set that's 50%, and if there's more than one, then you choose based on that? Because it may be that nothing really gives you exactly 50%. A lot of things are close. And I guess you'd have to decide which one of these to prioritize. Yeah. Okay. That's a great idea. Let's hear more ideas, and then, of course, I'm going to end up giving you, well, actually, we might not get to the optimal scheme until next time, but we're going to learn a lot anyway about this time. Okay. Any other ideas? Is that what everyone would do? Find the question that's 50% or close to it. You may not always be able to get exactly 50% of the probability. Okay. The first half. Now, are they given to you in an arbitrary order, or are you doing some sort of sorting, or what? So you're saying just you have a probability distribution, and you just go through and just try to get as close to half in whatever order the list was given to you. Or maybe you're thinking of sorting it according to probabilities and go to half. Either one of these are all good ideas. So this seems to be the main thing here, that you're trying to get a half, but maybe you're trying to figure out how do you go about getting a half. So maybe you do something like in order, choose set in order. You might do something like sort. But I mean, maybe if they give it to you in the right, if your scheme is just taking the order they gave it to you, how do you know someone didn't put it in the order so that it's going to be exactly the set he decided, right? Oh, I see. So you are kind of thinking of these being in sorted order somehow. Yeah. Okay. Is there any other ideas we should think about? And then you would just do the same thing the next time and the next time? Okay. Now, let's give at least a bound. What can we at least say we know? Whatever optimal expected length there is, we know that the expected length, I can say the optimal one, whatever it is. I'll put a little star here for the optimal L, okay, associated with the optimal questioning scheme. We know it's less than at least what we had before, log 2 of omega. That's what we said at the very beginning. You can get 2 to the number of questions if you just assign everything the same length answers, okay? In other words, if you don't do any optimizing, every item is treated equal, and you used your whole, log omega questions to resolve it. Let's say this means round up, because log might not be an integer, so round it up. We know we can design a scheme that gets us that. We're trying to beat that, okay? Great. So let me relate a questioning scheme to a code, because now all of a sudden we're going to see what does this really relate to information. Remember, we're moving to for this week and next week. We're kind of talking about things other than the Fourier transform. We're talking about right now compression of information. All right. So how is this related? It turns out it's very related. So a question scheme gives a code. We can have something we call a code that is associated with any questioning scheme. So let's look at the sequence of answers from a particular questioning scheme, like the one we came up with above. Okay, we have it a tree. It's no longer on this page, but there's a tree that kind of expressed what our questioning scheme was for this game between these 4 things. And I can say the following. For Apple, we had, let's go back here and let me label yes as 1. So let's say that yes is a 1, no is a 0. That's easier than writing yes and no everywhere. Okay, so what would the sequence be for Apple? 0, 1, right? It was no yes, so 0, 1. So I'm going to write that in this table here. So Apple was 0, 1. Those were the answers. If we saw that sequence, we knew we were at Apple. Orange was 0, 0, 1. Pear was 1. And banana was 0, 0, 0. Okay, I'm going to call this a code. All right, this is the code that tells us the item. Now, so in other words, some notation I might use, I might say the code word for apple is this item here, 0, 1. That's the code word. It's one item in our code. Code word for apple, okay, is 0, 1. All right. Similarly, the code word for orange is here. ... Okay, so these are the code words, and the set of code words is the code. Now, there's something interesting to notice here. Notice that so any system of questions implies a code, right? That's what we just did. We kind of translated our system of questions to a code. But the opposite is also true. So the code that I've written above actually tells me what the sequence of questions was. So notice the code is the whole scheme. All right. How does the code tell me what the sequence of questions is? Well, all I have to do is look at the first answer. This first entry in the code was the answer to the first question. So now I know what the first question was. The first question was, is it a pear? That's the only question that would have these answers, right? Now the next question, I'd look at this next row, and I would say, okay, the next question is it an apple? Now in general, it would be a little more confusing because you'd have multiple ones and multiple zeros. And so the question would be, is it in this set of ones? Okay, that's always going to be the question. So in other words, once we've written the code, we actually know what the questions are. You just look at the first entry and say, is the first bit of the code word a 1? That's the first question. Okay, it's like we could play this game in a weird way. I could write out a big, huge code, and I could say, is the first bit a 1? And you'd say yes or no. It's a yes/no question, right? And I'd say, is the second bit a 1? Is the third bit a 1? And I'd stop once I know which one it is. And it's the exact same thing. It's just I've restated the same questions. Okay, so now we can see this is getting a little more towards something general with information. Now let's talk about what requirements are there in the code in order for this to be valid, for you to be able to, end and know what the answer is. Because you could always just design a code, meaning just assign some sort of mapping from every item to binary sequences. That's a code, but it's not always going to work. All right. So what do we actually need? Let's just start listing some requirements. What would we need from this mapping? This mapping that takes items in your set to code words. What's one requirement? Yes. Only one per what? Only one. Only a single one in a column. So you're saying this is the column. Only a single one. However, we know we could have had more than one, right? That was just our particular thing. Yeah? Okay, perfect. So we need it unique. That's for sure. Because if two code words were the same, you're not going to be able to tell, no matter what happens, which one of the answers it really was, right? Okay, so now this is necessary, but it turns out it's not sufficient. And I'll give an example here. So suppose that you have the following code. We're going to have, again, we have apple, orange, pear, banana. And we're going to assign these code words 0, 1, 0, 0, 0, 1. These are all unique. Okay? It needs to terminate with a 1. Wait. It needs to be all zeros or terminate with a 1. Okay, you're getting to the requirements, but not directly. So first of all, let me just make sure it's clear why this doesn't work. What's the problem with this thing? Yeah, go ahead. Exactly. So if you see zeros, say 0, 0, you don't know. Is it pear? Is it apple? Is it apple and did I go on to the next thing or whatever, right? So there's a problem with that. You don't know. When you get to 0, you don't know, should I stop and say it's an apple or should I keep asking questions? Okay. All right, so there were some ideas about how it terminates. There's actually there's a requirement that's going to be even easier to understand that's actually going to be what you want in your code. Okay, prefix free. So let's look at this condition. And people call this a prefix code. It means it has no prefixes. What do I mean by that? It means that no one code word is a prefix of another code word in the code. So for two different entries in your code, you can't have one being a prefix of another. That's exactly what happened here. Apple was a prefix of pear because the beginning of pear has a 0, and that's the whole code word for apple. Okay, because if that happens, clearly you know that you're going to once you reach the prefix, you don't know, should I stop or should I keep going in that sequence of questions? And conversely, if you do have a prefix code, if nothing's a prefix of another, once you see the code word, you're done. There's nothing else that could possibly still be alive in your question, in your scheme. Okay, so that's really what we need here. Okay. All right, now let's turn this into a real concrete data compression problem where we're just talking about codes, but you can always retain this idea that this is just like the questioning game. Any code is like asking questions. Anytime someone transmits you some bits of information or you start reading out of memory, those are answers to certain questions. A question of, oh, is that bit going to be a 1 or a 0? Oh, it's a 1. Okay, right, and that tells you something about the data. All right, so let's now think about you have a sequence of observations from some distribution. You can think of these like letters in a text, okay? But we're going to imagine that they're randomly generated and that you know the distribution from which they're generated. They can be, these can be any finite set of values, the x's. So it's still like the 20 questions game. You have, for example, these might be items on a shopping list or something, and you know the probabilities that they occur, each one. But you have a long sequence of them. Think of them like letters of the alphabet. Okay, so you have someone typing. Just imagine that each letter is, for the sake of this, what we're going to discuss right now, each letter would have to be independently typed. So it wouldn't really be the English language because you have a lot of correlation between neighboring letters. Okay, it would be like, oh, E's the most frequent letter, so that appears most often, but you just have a random sequence of letters according to their frequencies. Just imagine that for now. Okay, we want to know. So let me actually write. So that's one example, is letters. Letters of text. Another example would be the output of a quantizer. We talked about a quantizer last time. So say you quantize, like we talked about with sound. CD audio quantizes at 16 bits. The output comes. But suppose you know that some of these values are more often than occur more often than others, and we might want a better way of storing them. Okay. So what we're going to do is design code that are binary sequences, just like we've been doing, of arbitrary length. And we're going to use those to store this sequence Okay, so this just means binary sequences. Of any length. Of course, what we're going to want is that when we store these things back to back, so we're going to take C of our first observation, C of the second one, C of the third one, we're going to concatenate these, right? Concatenate their code words back to back as we store them or transmit them. And we need you to be able to, at the other end, peel them apart and get back the items, x1, x2. So we want this to be, we want it to be, have some properties so you're sure you're able to decode it. So let me state these properties. One property you might ask for, it's very related to what we just talked about, non-singular, and that's exactly that unique property that we said above. Every code word should be unique, but now we're going to call that non-singular. That's what they're called in this context. So that means that any two codes are different. If X and Y are different, then the code words are different. So this would imply that you could decode if there was punctuation in the sequence of stored bits. Let me tell you what I mean by that. If the way the bits were stored in memory or transmitted was that C of the first item was written, and then a comma was placed there, and then C of the next item was written, and then a comma, and so forth. If you had commas in this, so it's a binary sequence with a comma, another binary sequence with a comma, and the comma tells you when the next code word starts, then this is all you would need, non-singular. Okay? You would just need every code word to be different, and this type of code that we looked at up here would actually be fine. There would be nothing wrong with this if you had commas in your sequence. Okay? Because everything's different. However, in reality, you don't have these commas. If you're writing bits, a comma has to be its own symbol. So if you're doing everything in binary, you'd need a binary sequence to represent your comma, and that's going to end up wasting bits. Okay? So instead, so that's one thing you might ask for. But let's look at another property. I'm going to have 3 of these. All right. Now, you might ask for it to be uniquely decodable. This is really what we're after. We need it to be uniquely decodable. And this simply means you can decode without punctuation. And I'm not going to give a list of rules that would allow that. But thirdly, we have that you could ask for it to be a prefix code. And you can probably see that why the prefix code works in this setting where you've concatenated code words together. It has the property that it's instantaneous. So that means once you get to the end of a code word, you know you're at the end, even without punctuation. Right? So the code word ends, and you know it's not the prefix of anything else. You know the code word is over. Go on to the next code word. You didn't need a comma to tell you that. Okay? So if we take the idea from 20 questions, at 20 questions by the end, you always know the answer. All right? Then that would certainly be sufficient for this setting. But what's this thing in this middle, uniquely decodable? Is that more general than a prefix code? Do you think there's anything that's uniquely decodable that's not a prefix code? I guess that's the question. Because these are all subsets, right? Clearly, prefix code, if it's a prefix code, then it implies that it's uniquely decodable. And if it's uniquely decodable, it implies that it's non-singular. So my question right now, I guess, is do you think that this first relationship is both ways? If it's uniquely decodable, does it have to be a prefix code? It turns out it doesn't. You can have things that you can't decode until you look later. So you'd be reading the bits all the way into the future code words before you are able to go back and determine that this what x1 was. Okay, you can have those cases. All right. You can also think about taking your prefix code and doing it backwards. well, that could be decoded in reverse order, right? But it wouldn't necessarily be a prefix code. So it's still uniquely decodable. Okay, so uniquely decodable is actually more general than a prefix code. Yet I said we're going to focus on prefix codes. Why is that? Are we going to lose some optimality? So we focus on the prefix codes. Because there's actually no loss of efficiency. So although you can come up with codes that are not prefix codes that are still uniquely decodable, they will not have any different. You can always prove that you can come up with a prefix code that has the same code word lengths. Okay? So in fact, it wasn't necessary to generalize to the uniquely decodable one. You can just look at prefix codes, not lose any efficiency whatsoever. All right. And prefix codes come with this added benefit that you always are able to decode immediately once you see the end. All right, so that was all to kind of give you another take on why are we looking at prefix codes. We started by saying prefix codes are the scheme for 20 questions. Now we say, actually, if you're doing data compression, if you see a bunch of images or whatever you see, let's assume now they come from some probability distribution, and you want to assign code words to those objects so it can be decoded. Again, prefix codes are what we're going to look at. We want to choose a good prefix code. Okay, so next time I will actually give you the scheme for the optimal prefix code. Has anyone done Huffman codes? Okay, wow, a lot of people. Was that this semester or some other semester? Last semester. Okay, so Huffman codes, that's the algorithm for the optimal prefix code in terms of average length. All right, I'll give you some, we'll talk about it next time briefly, but let me approach it with what was discovered even before Huffman codes were known. We knew something about prefix codes. There were a few years between this question being posed and Huffman coming up with the answer. And here's something we can say immediately. Any prefix code has a following condition, which is the Kraft inequality. All right. So that is that if you do this sum over all your code words, if you sum 2 to the negative length of the code, that's always going to be less than or equal to 1. So this is a condition saying your lengths can't be too small. Right? We know the lengths can't be too small, but this is actually a very tight condition. It's saying, this particular sum always has to be less than 1. Now, how do we know that? Let's just convince ourselves this is really true. It's not too hard to see. For any prefix code, well, okay, I'll give an argument why this holds, but it has to do with the fact that any prefix code can be embedded into a binary tree. Okay, the leaves of this tree are the objects. Now, this is not anything new because we did that at the very beginning, and it made perfect sense to all of you. We made a tree for a questioning scheme for 20 questions. All we're saying is that that's true. Any prefix code has such a tree where you split with your yes or no. If the answer is yes, go here. If the answer is no, go here. So we'll label these with 1s and 0s in the code. So it does stuff like this. And each of these splits with a 1 and a 0. And so you have some tree that expresses your code. All right? And the items are the leaves of the tree. So that means, let's say there were 6 items in this set, omega. And one of them is here, x1, x2, x3, x4, x5, x6. Okay. This is a way of listing your code because the code word for x1 is 111. Code word for x2 is 110, and so forth. And clearly, you don't have any prefixes because that's what the tree does. It prevents you from having prefixes in your code. Okay. Now, what if we go to the depth of the tree? So consider this depth 4 in this tree. and extend everything out to that depth with these phantom edges. Because remember, the objects were the leaves, but I'm going to just keep the leaf going and make branches. Okay. Okay, then I get these sort of phantom nodes here. And of course, we know how many would have been. So here's what we have. We have that there are. How many phantom leaves will we have? Well, 2 to the L max. L max is the depth of the tree, right? The maximum length in our code. That's how many of these phantom leaves we have at that depth. But now let's say how many of those leaves are attributed to each of the objects here. Because really, some of these phantom leaves branch out of one of the leaves, right? So we could do some accounting. And we could say, here are our phantom leaves. We know they add up to 2 to the L max. But we know from x1, we got 2. See, 2 of them. From x2, we got 2. From x3, we got 1. From x4, we got 1. From x5, we got 2. And from x6, we got 8. And these, like I said, these should sum up to 16, right? 2 to the L max. Sums to 16, right? Okay. But how do we know how many they got? Well, this is, in fact, 2 to the L max minus the length of that particular code word. Right? Okay, so in fact, the amount of phantom leaves that come from each object is this formula, 2 to the L max minus the length of the code word. Okay, and since they can't add up to more than, so that means if we add all of the phantom leaves up, we sum over x. 2 to the L max minus the length of the code word. And we know that can't be more than the total number of phantom leaves you can get, which is 2 to the L max. Divide both sides by 2 to the L max, you get Craft inequality. Okay, so it's that simple. Now, why is it an inequality rather than equality? Well, you could have had an inefficient code. So you could have done something silly. In your original tree, what if you had moved like x6 to this leaf? Okay, that would be an inefficient code because you could have stopped once you got to this leaf, but instead you asked another question for no reason, right? But that's okay. It's a valid prefix code. And you would see that when you do this accounting, you would only get 4 from x6. So really, these are like upper bounds on how many phantom leaves you could get. Or, well, they're not upper bounds. They're the exact amounts, but you might have branches of the tree that just have no terminating object. Okay. So that's why it's an inequality. And that gives us something to take away from this. So here's a summary. All right. The summary is, 1, any prefix code. Prefix implies this Craft inequality. All right. Second point. Okay. If you have Craft inequality satisfied, if you can choose a function L of lengths that satisfies this inequality, then there exists a prefix code with lengths Lx. So in other words, come up with any integer function, L of x, that satisfies Craft. And yes, there is a prefix code for it. So really what that means is Craft kind of encompasses the entire problem here of designing optimal codes. And lastly, if the Craft inequality is loose, meaning you don't have equality actually, then in fact the prefix code is not optimal for any, no matter what the distribution was, is inefficient, because that always amounts to a case where one of your code words can be shortened without hurting any of the other lengths. Okay, so that's our summary about Craft, and that will be where we start next time as we look at how long the average length has to be.